got you. All right. Okay, our next speaker is Madelyn Broome. Madelyn earned her bachelor's at Princeton and her master's at Cambridge working with Ollie Shortall on protoplanetary disks. She's currently a fifth year at UC Santa Cruz working with Ruth Murray Clay on exoplanet theory. She primarily works on modeling atmospheric escape, but she is soon to be transitioning to rocky exoplanets and is also interested in statistics and astrobiology. Her talk is entitled WinAE, a fast 1D atmospheric escape model with X-rays and metals. So with that, go ahead and take it away, Madelyn.
Thanks so much, Tiffany. Hard act to follow up, some really neat stuff. We're going to go from some very recognizable physics to some very extreme physics here with atmospheric escape. So I spent the past 5 years developing a 1D atmospheric escape model called WinD. And that little sticker of now with X-rays and metals, we'll get into why the X-rays and metals are important to this process. But first, let's do a quick overview of what atmospheric escape actually.
Was that her internet that cut out?
Yeah, Madelyn, we've lost you.
Oh. Okay, Madelyn, we lost you for about 10 seconds.
Okay. It said my internet connection's unstable. Dang, Ed Jerome. All right, to recap, atmosphere, when atmospheric escape folks say atmosphere, we always mean everything above RP, so everything above the slant path optical radius. So the 3 main regimes of atmospheric escape are boil-off, which happens in the first megayear, an extreme process of mass loss. Core-powered mass loss, which is driven by the intrinsic heat of formation, where the effective temperature is high enough to drive an outflow. And photoionization-driven, which is also called photoevaporation, mass loss, which is especially strong around young and active stars because it's driven by XUV or X-ray and extreme UV radiation. But it's not just the early planets that undergo this. It can actually be ongoing throughout a planet's life, hence why we're interested in this process, and it can drive observable outflows. So in pictures, what this looks like is when we have a close-in planet, so a planet with a period less than 100 days, as it cools and contracts after having undergone mass loss previously, eventually these X-rays and EUV rays can penetrate deep enough into the planet's atmosphere that it can no longer efficiently cool the energy deposited, and it begins to heat the atmosphere, driving a pressure gradient-driven wind called a Parker wind. And a Parker wind is a transonic Parker wind specifically, which is a particular solution where it goes from being subsonic to supersonic outflow at a certain point called the sonic point. And significantly, this is not driven by the effective temperature again, but by heating due to photoionization. And a significant note about X-rays and EUV rays is that EUV photons have enough energy to ionize at least one species in the atmosphere. And X-rays specifically have the energy to ionize more than one species in the atmosphere, which is why it's important to pay attention to X-ray physics. So, while this originally came from theory, the idea of atmospheric escape, it has been seen in exoplanet demographics. And so we have these classic exoplanet demographic plots, our period and mass on the left and our planet size versus number histogram on the right. And these two features are not indeed completeness issues. These planets are actually missing. And what it does, even though atmospheric escape is not the sole architect of these demographic features, it is definitely a contributor, which tells us that mass loss is an important part of the evolutionary history of these close-in planets. We also see some more direct observations of atmospheric escape. So on the left, Lyman alpha line broadening is when the fast-moving neutral hydrogen flowing off the planet is able to Doppler broaden our Lyman alpha line, get it out of that corrupted line center where we can't trust the information because it's interfered with by geochronal emission and ISM absorption, and gets it out here so we can estimate some velocities. But importantly, we cannot estimate the velocity of the outflow very close to where the outflow is launched, which means we can't back out mass loss rates from Lyman alpha emission line broadening alone. There are other features. We can look at metastable helium transits. That's the helium 10-830 angstrom line. And we see this classic atmospheric escape lopsided transit shape where you don't just have a planet transiting, but a planet and a forward or backward tail, or perhaps a tube coming off of both sides. But because this is metastable helium, in order to get an accurate mass loss rate from this observation, we would have to do a full thermal calculation that requires making a lot of assumptions. So we can't directly observe mass loss rates. We can only infer them from models. Hence why I've spent the last 5 years creating such a model. Before we get into what we need out of a model, let's figure out what exactly we need to get out of a model. I realize that was a tautological statement. Mass loss rates are specifically calculated from the radius, sonic point radius, the density at that sonic point radius, and the velocity at that sonic point radius. Reminding everyone the sonic point is where that outflow goes from subsonic to supersonic. And so we need some way to calculate that sonic point radius and the structure of an outflow. So that's what WinD does. It's 1D, where 1D is the substellar point. Multifrequency, meaning we can put in a custom stellar spectrum that can range over those EUV and X-ray photons. Multispecies, we have the ability to model metals. This is hydrodynamic, so we are solving the fluid equations, the energy, mass, momentum, conservation equations, as well as the ionization balance. And modeling this as a Parker wind, which means it's a 2-point boundary value problem, which means we can efficiently model it using a relaxation model. But why do I keep mentioning metals and X-rays? Well, earlier we heard that young hot stars are strong XUV emitters, but also metals have large X-ray ionization cross-sections. C, N, O, Ne, Mg all have what is called K-shell ionization, where their cross-section here in the green line becomes extremely large relative to more abundant atoms like hydrogen at high energies. And so that'll interact interestingly with X-rays. And also, planets are likely supersolar metallicity. In the Thorngren et al. 2016 plot on the right, we can see planet mass as a function, metallicity as a function of planet mass. And pretty much all the planets are expected to be supersolar in metallicity. And indeed, though our Lyman alpha and our helium transits were limited, maybe metal transits would be a more direct line to estimating mass loss rates. So what can we put into our model and what do we get out? So we have the ability to control our planet parameters. So mass, radius, semi-major axis, stellar mass, stellar luminosity, the metals and the metallicity in the atmosphere of the planet, the input stellar spectrum. Most of the ones you're going to see today are scaled solar spectra just for ease, because it's a little difficult to get fully reconstructed X-ray spectra, and the boundary conditions of our inputs. And what you get out is a temperature, density, velocity, ionization fraction, and column density, which is a proxy for optical depth, as a function of radius. And that's going to allow us to calculate mass loss. Limits of such a model, a 1D model like this, are that it is steady state again, so it's number time evolving. We don't include diffusion or drag, which is appropriate for all the simulations I'm going to show you here, because all of those species are not abundant enough to be over the crossover mass. So they're going to be evenly lofted and dragged throughout without any sort of diffusion in the outflow. We ignore magnetic fields. Magnetic fields are hard. Their impacts aren't clearly understood on outflows. And because this is 1D, our assumptions are only going to be valid up into the Coriolis radius, the turning radius, where our outflow is then going to turn and travel along flow lines into a cometary tail or a tube or a frontal cometary tail. So once again, in pictures, if we have a stellar spectrum, such as the one here, which is smoothed, coming into our atmosphere, we trace where those photons of different energies are absorbed. And specifically, we calculate with our relaxation model everything below some lower boundary condition here, which we set to be about microbars. So we capture all the absorbed radiation. At some point, this wind is going to launch. It's going to launch upwards at subsonic speeds until it hits the sonic point, and then it outflows at supersonic speeds, allowing us to use an OD integrator to solve for the rest of that. But when we're calculating mass loss rate, we're really only concerned with this relaxation region here, so between the lower boundary condition and the sonic point. So for energy conservation, just to give an insight into what terms we calculate when we do our energy conservation. We calculate below the wind as dominated by bolometric heating and cooling, because this region should be largely molecular. And this allows us to agnostically compute a lower boundary condition. So rather than having to guess at the temperature and density at a certain pressure, at the microbar pressure, we're able to calculate it from the balance of bolometric heating and cooling, which is pretty nice. Then WinD solves for where the radius, or for where the wind launches. And then above it, it calculates the energy as a balance of advective heating, the heating due to ionization, line emission, line coolings, which is Lyman alpha, and when you have metals, O and C line cooling. PDV works, that's the work due to expansion, recombination, and eventually maybe things like H3 plus cooling. So why go to all this trouble? Why use these models, ones that are beautiful and sophisticated and maybe expensive, or ones that are maybe a little less beautiful and sophisticated, but quite fast like ours? Still, nothing is as fast as using the energy limited mass loss rate approximation. And this is commonly used. This is the idea that 100% or some efficiency of the photons coming in are absorbed some radius r, and then 100% of that energy, or again, some efficiency epsilon, is converted back out into an outflow. And so the energy limited mass loss rate is just a function of your incoming flux of XUV photons, your planetary mass, and this radius at which they're absorbed, times some tidal correction. Well, most folks assume for ease that this value is RP, that's where our photons are being absorbed, and that the efficiency is somewhere between 0.5 and 0.4. But where is the energy actually being absorbed in these planets' atmospheres? So most of the plots I'm going to show are going to be the quintessential system, HD 209. It's an older star, so low flux, and this atmosphere we're seeing is going to be just pure hydrogen and helium. So to start out with, what if we put all of our energy not into a multi-frequency spectrum where we have the sophisticated X-ray physics and metal interactions to think about, but just into monofrequency 20 eV photons? Well, if that's the case, we see that, the only line I want you to pay attention to here in this plot of energy as a function of radius is going to be the red line, and that's our ionization heating. And so you notice that the ionization heating peaks pretty much around where tau equals 1 for the 20 eV photons are, so where these photons are being absorbed. And it's quite nicely confined. However, when we spread out that same flux across an entire spectrum, entire XUV spectrum, what we get is a much broader distribution of that ionization heating. We're less peaky here, and indeed, because we're depositing X-rays deeper into the atmosphere, warming lower, puffing up our atmosphere, we're actually going to get our 20 eV photons absorbed much further out. And so we're spreading out the deposition of the energy and changing where our wind is being launched. And so before I show the next plot, I'll remind folks, when we care about predicting observables, we care about a couple of these values. For Lyman alpha, we care about the velocity and the ionization fraction. When we're looking at metastable helium transits, we're looking at caring about the ionization fraction and the temperature. So these are profiles of density, velocity, temperature, and ionization fraction. And here we're plotting in black a pure hydrogen atmosphere. This is again for HD 209. And in green, a solar metallicity atmosphere with H, He, C, Ne, Mg, and Si. Oh wait, actually no Si. And so these are a lot of plots to take in, but notably what you can see off the bat is that our velocity is going to be slower, our density is going to be lower, our temperature is going to be lower. Where we're depositing the energy is going to be slightly different with the presence of metals. And what we predict the ionization fraction of hydrogen to be is going to be different with the presence of other metals. And so that's going to affect our ability to predict what these observables are going to look like. So even when we want to predict these well-known observables, we want to think about things like the metallicity of the atmosphere, the presence of metals, and the presence of X-rays. And notably, I'll highlight here, the mass loss rates are quite different for these. When we include metals, we get a lower mass loss rate. So indeed, we have these larger ionization cross-sections absorbing more of this energy, potentially that could heat us more and drive a faster outflow, but ultimately metals weigh more. And so that is going to cause us to have a lower mass loss rate. So when is it appropriate to use that energy limited mass loss rate? You don't always want to pull these sorts of tools out of the closet and download some new code and learn how to use it. Well, returning to this equation, we'll remember that the way we typically calculate energy limited mass loss rate is as a function of RP, the slant path optical radius. So to introduce some mass loss grids, these are for pure hydrogen helium atmospheres, no metals. Plotted on the left is a low flux star, so an older star, and on the right is a younger star. And there's some patterns that are already quite evident that make sense. You know, we're going to have a higher mass loss rate when we have more flux. But notably, it's not sort of infinite that you pump in a higher flux of photons and you're going to get a higher mass loss rate. So on the left, we consider most atmospheric escape in the low flux regime to be what's called energy limited, which means if you added more energy, more flux, you would get more mass loss. But notably, when you have a high flux, you've sort of reached the maximum amount of energy you can put in and expect to get more of an outflow out. And indeed, you are then limited by what's called recombination limited. Your irradiative line cooling, for example, Lyman alpha cooling, becomes very efficient, and it sort of attenuates your ability to increase your outflow rate or your mass loss with a higher amount of flux. So in the energy limited case, if we compare these values then to the energy limited mass loss, let's look on the left first and note that red is overestimating, and when energy limited mass loss rate overestimates the actual calculated mass loss rate, and blue is when it underestimates. And we see in the low flux case that indeed, energy limited mass loss is going to dramatically underestimate the mass loss rates for super Earths and sub-Neptunes, where this here is a Neptune-sized planet, and our little orange dot here is HD 209. And it's going to overestimate by a little bit for very large hot Jupiters, though for typical hot Jupiters like HD 209, it's a pretty decent estimate. And in the high flux case, the reason we don't see it underestimating and always see it overestimating is because, again, these are recombination limited outflows. They're not energy limited. And so energy limit is, if in fact, estimating it to be a more efficient process than it actually is. So focusing just on the low flux case, what if instead of calculating energy limited mass loss rate at the planet's surface, but at RxUV, at that wind launch radius, the one we saw that was affected by the presence of X-rays and metals, if we calculate the energy limited mass loss there, we find that it is actually in much better agreement with our calculated mass loss rates. So if you want to use energy limited mass loss rate, you probably want to do it with the actual efficiency, which is something around 0.2 for super Earths and 0.3 or 0.4 for hot Jupiters. And you want to calculate it at this RxUV. Unfortunately, getting RxUV does require these sorts of models, and so you're kind of stuck back in the loop of you probably want to use these models, and or I need to pay an undergrad to make some lovely grids that the field can use and extract these mass loss rates from. So that's windy in a nutshell, and what we've been able to discover about the energy limited mass loss rate. But because we have these outflow profiles, because we have the ionization fraction, the temperature, the velocity, the density, we're able to make some predictions about observables. So I'll ask folks not to share this because this is work in progress, but there is one example of an outflowing atmosphere for a hot Jupiter around a K-star, HD 189733b, and it has this mysteriously deep X-ray transit, where the transit in the optical is these dots here, and that's a 1 to 2% transit. But then for some reason in the X-ray, it's actually a 6 to 8% depth transit. And early on, this paper identified that, well, that could easily be atmospheric escape. This planet is at 0.03 AU. It should probably be undergoing atmospheric escape. And so they did an order of magnitude using the energy limited mass loss rate. And they said, well, probably to get a tau equals 1 surface to slant path XUV photons to be as large as we need to obscure 6 to 8% of the star, we're going to need this huge mass loss rate of 10 to the 11 grams per second. Well, we were able to run this through Windy, and notably, you don't actually need all of your outflowing material to be concentrated at tau equals 1 surface. We, in fact, are able to get the obscuration needed with just a mass loss rate of 10 to the 10 instead of 10 to the 11, because we're getting absorption not only from the tau equals 1 surface, but from cumulatively from all of the absorption all the way out to the limits of our model, the Coriolis radius in blue. And because this planet is pretty well constrained to be 3 to 5 times solar metallicity. We're actually able then to calculate the depth of the transit in this sort of boxy way they have with none of the transit shape, but just the transit depth indicated. And in yellow, we can see that the 1 times solar, too shallow. 1 times solar, sorry, with everything, still too shallow. And then indeed 3 times solar metallicity seems at this point to recreate quite well the depth of the transit at 6 to 8% in XUV photons. And that's actually just with the spherical extent of the planet, not including the cometary tail. So we may find it to be even deeper. And these ability to predict observables has been used in a couple of other means by co-authors. WASP-12b is another close-in hot Jupiter. There had been a previous hydrogen alpha detection. One of our collaborators at OSU, Anusha Payas-Nodkar, used the PEPSI instrument and did not detect H alpha. And indeed, our model, WINDY, showed that, that we are far below the detection, or the observable outflow should be far below the detection limits of PEPSI instrument. And then a neat Nature paper one of my co-authors put together is these 2 planets, TOI 776b and c, which are on either side of that period radius valley, so may have different evolutionary histories, that indeed the mass loss rates for these planets are consistent with losing a predominantly hydrogen atmosphere and not losing a steam atmosphere, which has implications for the evolution, for the role of hydrogen escape in the evolution of these planets. And so to recap, we've covered how XUV radiation photoionizes atmospheres of close-in planets, those with periods less than 100 days, which can drive these observable outflows, and that the wind structure and mass loss rate is going to be sensitive to the inclusion of X-rays and metals. At low fluxes, your energy limited mass loss rate calculated at your wind launch radius, where most of your XUV photons are absorbed, is more accurate than your mass loss calculated at the planet's surface. And that's going to dramatically underestimate the mass loss for super Earths, slightly overestimate for large hot Jupiters. It's pretty okay for typical hot Jupiters. And the outflowing metals may explain that unusually deep X-ray transit for HT 189733b. And in the future, we will be creating some of those grids, including exploring the impacts of higher metallicity, especially on rocky planets. So I'd like to give special thanks to all of my co-collaborators, and particularly to my cohort of the ExoExplorers and to our Exo guides as well. And if you are interested in checking out WINDY or using this tool for your own purposes, you can scan this QR code or visit the GitHub link, and it is in a beta version right now. So thank you.
Awesome. Thanks so much, Madelyn, for a great talk. All right. Any questions for Madelyn? You can use either the raise hand tool or the chat. Yeah, Leo, go ahead.
Leo.
Hi, Madelyn. So my question is, so I'm an observer and I observe atmospheric escape, and one of the biggest mysteries that we've been dealing lately is that when we look at single line species like helium, for instance, and we observe them, we have a detection, and we try throwing some models at it. It seems that our models predict much deeper signals than what we actually observe, and many people have started talking about metals potentially cooling the outflow, making the mass loss rates lower, and that could explain the signals being shallower than we expect. However, you can also make shallower signals if you simply decrease the helium abundance in the outflow. So it seems to me that there's a degeneracy between helium abundance and metal cooling. Is there a way to break that degeneracy to fit our observations?
So I want to give Leo a shout out. He's used this tool, WINDY, to do really cool predictions about how we'll be able to predict metals with HWO in 2045. So look forward to that, hopefully one day. But no, that's a really good question, because I think it would require making lots of grids, essentially, where we modulate things like helium abundance and the effects of metal cooling on
Yeah.
dampening the outflows. I think it really basically is going to be a parameter search question. Right now, it does feel like we'd probably be able to distinguish that. The degree to which we could confidently say which is the predominant driver or the prominent source of that, I think we'd actually have to do the calculations to figure that out.
Yeah, and observing signals in many different species, not only in helium.
Yeah, I think that's why I'm really excited about HWO
Yes.
and future instruments, is because if we get the ranges of spectra and the resolution we want, we should be able to see more of these metal line transits in the future, which is exciting.
Yes. Yeah. Thank you.
Other questions? I guess I'll ask one. You alluded to other, you talked about HWO. What other future missions are you excited about to further constrain this problem from ground
There's
or
a couple
space?
teams working on, that's a great question. And unfortunately, it's just dreaming right now because there's a couple
Yeah.
teams working on getting UV instruments, far UV instruments approved by NASA. There's a couple of teams that are working on instruments that'll be just a little bit too long of wavelength to capture a lot of the stuff we care about, like the Lyman alpha. And so the dream is that whoever gets their UV instrument through the medium or small project will get the wavelength range that we want, which is the extreme UV.
Okay. All right, great. Okay, any last questions? Anybody online or in the chat? All right, if not, let's go ahead and close this Exoplanet Explorer seminar series instance.